Wow, a live stream. Isn't that amazing? We are live. Let's see if I can put the view count on my screen here, which you can see, as well as the Discord chat. So, hello. One viewer, is that me? No, it's not me. It's Aditya, I guess. Hello. Staunch supporter. Now I have 0 viewers again. Just 1 second. Make this window smaller. Here. There. Okay. Good day to stream. Good time to stream. Good universe to stream. It's not a good universe for anything. We live in the pain dimension, as I always teach. But even in the pain dimension, you don't always have pain. It's just something that comes and goes, hopefully for you too. So, we will work on our website, which is still half baked as always. Building a knowledge base. And we are doing audio, and we are doing image recognition. And, oh, a lag. Let me check the analytics. Stream is healthy, but video resolution is not optimal. I think the stream is fine, actually. I can't do anything else right now, I think. I could go to lower latency, higher latency, actually, if it's buffering. I don't know. It's strange stuff. I don't think it's anything from my side, actually. I have like 7 FPS in the camera, but that's a different thing. Yeah, so audio and image recognition. And in the image realm, I think I made a major breakthrough. Like this, it's a new architecture that is compressing the image in a way that gives us semantic information. Like I have any image, I have this image, a screenshot, and there is like, there's white space, there is lines, and the lines form rectangles, there's font, and each of these things can be compressed into some code. We actually allow any code in the decompression. The compressor makes JavaX source code, so it can use any JavaX function. And the idea is to have the source code that's generated shorter than just having the raw image data as a hex string. So like 1 byte gets converted into 2 hex characters, and that's all baseline. It's just the image as raw pixels. So we don't want to allow any. We don't want to do random compression functions or decompression functions. We want to select them such that they are useful for semantics. If you just take an area, right now the algorithm takes just makes squares over the whole screen. That was really poorly expressed. It makes a grid of the screen such that we have squares of a fixed size, and each square is compressed separately. And And when one square is just one color, that's just stored as repeating color, and there's certainly a good semantic compression also. If something is just one color, that's the way to compress it, and there's not much else to say. And when all these cells are compressed, in the next step, which I haven't done yet, we can start to have these cells connect to each other. If two cells side by side have the same color, they can merge into one, improving the compression and also being a better semantic result, because now you know there's a larger white area. And in this way we want to continue, and then also detect lines and things. And the compression is like a helper for it guides the whole recognition effort. And the compression is a search. So you start the compression, and it will compute, and eventually we'll probably have so many algorithms that it never technically completes, but it just doesn't find any better results anymore. And there's a probability measure, because everything is a probabilistic machine. So we have one central probability number. If I was working on the image recognition in this stream, I could show that maybe. It's probably fun to look at, because you start with probability 1 and it counts down. So if it's at 0.5, then you know that things that are calculated now are half as probable as the maximum. It's all an estimate, but the further the number goes down, the more you can expect the search to be actually complete, or mostly complete. So that's very interesting. I don't know how many more elements I need for this image compression, but it's not that many elements, I think. And then we should start to see some good results. One other thing it will find is repeated elements. If you have an icon that appears multiple times, that will also be found, and then that's a very good semantic information. Yeah, I think I hit the jackpot with this new architecture. The idea of compression, finally it came to me, and then it was the missing piece. So the approach is called recognition by compression. There are all those guys that say AI is only compression, and now I'm joining the choir, but I think they were missing a few points, because you want this semantic compression. There's another guy who also does AI by compression, but he only looks at the compression algorithm. He takes 400 megabytes of Wikipedia text, the usual, and says I compress this down and I compress it down, and the more I compress, the closer I am to AI. But my question is, how do you make the AI out of that? I've asked this a bunch of times already, because he never talks about that part. He never talks about how his compressor is going to turn into an AI. And my approach is to do both things at once. Compression and recognition in one step, so we are getting results quickly. Yeah, audio is the other thing, and audio we treat actually just as an image recognition, or mainly. We convert audio into an image and recognize that image. And let's see if we can wire these frequency images in a nice way. Let's say, yeah, the basic thing is just called frequency image. And it actually grabs its own demo image, or demo audio file. Oh yeah, I'm talking on the Discord chat, but right now the YouTube chat is on screen, so it's a bit confusing maybe. Okay, this is an example. This is just some noise I made. This is the frequency image. Now using my own conversion, I had used another tool before. Well, this one we can control better, because it's all my own code, and I know what it's doing. And what it is doing is it takes all the frequencies that are in a piano. An 88 key piano has 88 frequencies, AA tones, and I take all of these and I put a half pitch in between. So I basically double this, and that's all the frequencies we have, and every frequency is one row in this image, one pixel row. So on the vertical axis there is frequencies, and on the horizontal axis there is time. And the idea now is to convert this back into audio, because that could be one way to make AI speak. You take what somebody says, you find the parts in it, you modify this here, you convert back to audio, and you get new speech that is modified but sounds like a person speaking. But the question is, how can we get from here to the audio? Because this is not really made for it. On the time axis there are overlapping windows. Every piece of audio is like connected. A part of it is computed again for the next pixel, because that gives a nicer image, I think. But if we convert that back, we count cap frequencies multiple times. And also the time resolution needs to change per frequency if we want to be really exact. If you have a bass, a vibration, bass tone, it has very few periods per time. So the resolution on the x-axis can be low. But if you have a very high frequency up here, it has many periods per time interval. So it would need multiple values per what is a pixel here. So that's also something we need to change. And maybe it's going to be two different architectures, one for just the frequency generation, being as quickly as possible, and the other one, slightly different conversion if we want to convert back into audio. And the fun thing I want to see is how bad the conversion back actually is. We could also try to just convert this back into audio, and it may be horrible or be not horrible. I don't know. I haven't tried yet. It's gonna be interesting. And one more thing I realized is that currently we are testing for square waves, because it's computationally very cheap. We analyze the input for the audio input for frequencies, but we don't take sine frequencies like you would normally in an FFT the correct way, but we just take the square waves because they're much cheaper. And this is also a question, does it affect this when I convert back to audio? But I also realized you can have an approximation of sine waves. If you take 4 sample points, you can start to approximate a sine wave. Have a good compromise in the complexity. So yeah, what would happen if we try to convert this back? Well, the idea was we make a new function, and it just has a number of oscillators which are all running permanently and are precisely accounted for. The clean way to have this revertible audio analysis. So I'm going to try to do that. Frequency, image. Yeah, these are all the parameters. Here the halftones are put in between the piano frequencies. This is the main audio analyzer. Sliding window, okay. Yeah. I had another one before these. It was called piano sampler. This was more complicated but pretty elegant, because you could feed in a new audio sample and it would do exactly those computations that are required for this new one audio sample. So any oscillator that changes its state just at this point in time is going to be calculated and nothing else. That was pretty elegant actually, but the whole class is a bit complicated. I think we can start with this one anyway. Continuous oscillators. Yeah, now the programming starts, so everybody who's not a masochist can tune out. I mean, you don't have to do anything, you can still listen and enjoy someone torturing themselves with coding. Although this should be fun. I mean, maybe fixing some bugs is not fun, but the purpose of this code is actually interesting. Yeah, image common. We forget the idea of the image for now, and all we do is the actual oscillators. So I think this class has all the components. Every oscillator has a frequency. It knows where its current period starts, and it records all intensities in the past using a time range and a complex number, basically. You have a complex number because there's intensity and there's phase. The two things you need to identify to restore an audio frequency. What is this? Oh, it's the length of the period in audio samples. Okay, yeah, this is actually all good. And let's set up some example environment. Let's do some new input. Where's my speaking gazelle? Why is there nothing here on the home page? We should put something there. I think it was mouth gazelle. Oh, let's ask the knowledge base. Mouth. The domain is known. Gazelle knows its own domain. That's pretty good. It can search for a picture. Okay, yeah. So that's the picture for mouth. Thank you so much. No, my question was where the demo function is, and I think it's mouth gazelle / demo. Yeah, that looks okay. And let's teach Gazelle about its own. Let's teach Gazelle about its own URLs. Yep. I don't hear anything.
Hello.
Okay. Recognize this.
Recognize this.
That's good. Let's go with this one. And what does the link look like? It's a long link, but it doesn't matter. And we have to calculate it somewhere. Maybe here. Piano sampler. No, we have a new one. It's called continuous oscillators. And we feed the audio. Opus streaming, yeah. I'm almost done with it. I want audio from the microphone to be streamed to the server via Opus, which is a good format, analyzed in real time and shown to the user again. And this is also almost happening. Very few little bugs remaining. Okay, does it grab its piano keys? Yeah, it does. It initializes itself with the 88 pitches. Not the doubled ones, just the 88. That's fine. So, how do we put in some audio? Yeah, something like this. Okay, zero set audio. How do we get our audio sample? What is this sound? I have a number of different interfaces for audio data. This should be the one, right? Static audio sample. Okay, yeah. What is it? It's an MP3. So, we get MP3 data. Yeah, I have to do some little page. I have to make some infrastructure. Not binary page once. That looks interesting. I will download the audio just once and then cache it. Oh, that's interesting. Yeah, the function does all we want. Very nice. Nice. Okay, file MP3. Then we say MP3 to wave. And that's how it works. The knowledge base should give us instant search for standard functions. At least that part is in MP3. Yeah. Nice one, right? MP3 to wave unless exists. That's okay. Why is it the website taking time sometimes? It could be DNS lookups. I don't know. Wave. Let's improve this function so it gives us a default file name for the wave file. Default place file extension with .wave. There. Now we should have a wave file. Let's print that. And then we just have to load our wave file. Wave decoder. Yeah, it's not a type yet. But we can make it one. Mm-hmm. Why does it have bugs? I thought I copied a working class. Step 2, window end. Oh, it takes a time range now. Aha. Fail. Oh, lots of fails. What have I done? What have I done? Did I copy a class that didn't work? Apparently I did. This used to work. Okay, that's ridiculous. That is not good. What am I copying here? This is completely like broken code. Maybe I abandoned the other one. I don't know. Okay, this does not seem like working code. Okay, it says developing actually. But I had something that worked. Let's try to find the working version of this code. Oh mama, what is it? Set start. Wow, this is full of bugs. It's not actually set start, it's called move to. One bug squashed. How many bugs can there be in these few lines? Many is the answer. Okay. Okay, the next time I call the method relocate, but it's still the same thing, I guess. It's still actually the method move to. And there was this other bug. And what's going on there? It gets a value for one channel. Audio can have multiple channels, as we all know. So, yeah, let's just take channel 0 for the purposes of this demo. Here you see macros, for example. By the way, I have macros in JavaX. Not that bad. Okay. Okay, same thing, one later. Fix that one. Complex channels. Okay. Almost done. I think this. Now we are almost done. Okay, complex channels, what is it doing? Of course, it has no comments, just a raw code. It takes this and this and this and makes this, okay. And turns out I just had a wrong type here, I think. Channels. Maybe. Maybe. Ah, very close. Measure this. Yeah, we want an even simpler one. Actually, we don't even want the sliding window. Normally, the audio analysis has a sliding window. I think for this one here, we don't actually need it. We just keep all the audio for now. Let's see. Yeah, let's put this one to null. And let's handle the null. Null value, the bane of the Java programmer's existence. Null pointer exception. Sergeant's null. That's 0. If this one is null, it is 0. And if they're both null, we just return null. Although this null idea is not super good. Let's do something better. Channels. All I want is a 0 value in all the audio channels. It can't be that difficult, can't. Where's my number of channels? There, and then we make a function we can reuse. And voila. Repeat value in all channels. Correct channels. Number of channels and the value. And this should work. It does. Okay. Aha, we have a WAV file. Perfect. Now, now we make an instance of this one here. I mean, this should also be a standard function, right? Wave to this one. Wave decoder. Yeah, we use 48 kilohertz now, because Opus is 48 kilohertz. But this wave file is probably a different sample rate. So we gotta check for that. Separate. What's our sample rate? Let's have it receive a file. It's buffering the stream anyway, that's fine. Bam. Is it closing the stream? Yes, it's closing the stream. Okay. Yeah, sample rate is 22 kilohertz for the computer generated audio. And I'm guessing we don't have a good sample rate converter. Sample rate convert. I mean, there's a science about converting audio between sample rates with minimal losses, and we do not have that implemented. But we should be good anyway. Or we actually change the audio analyzer to use a different sample rate. But I think that's confusing me. We should stick to one sample rate. So there's something here. Yeah, it does this simple thing. Takes short arrays. Extract mono samples. Samples 1. And we convert to our target sample rate, which should be noted in here. Okay. Let's see how many samples we get. Parameters in the wrong order. Definitely something the AI should help me out with as soon as it is smart enough. Okay, go again. Look at the free memory I have. I have 9 gigabytes of main memory free. My great ThinkPad has 16 gigabytes of memory. The best investment. Getting enough RAM for your machine that's the best investment. Come on, this was just, it was not even, it was just, you know what I mean. We need more AI in compilers. Okay, almost there. What did I do here again? Boom. End minus start. Does it tell us how many samples we are supposed to get? It should actually specify the data length. What are data bytes? Are data bytes the wave bytes? I guess they are. So, total samples. Channel. All this naming. Remaining gigabytes. I call it value. A value is a one number, like one channel amplitude in one time, one spot at time. Value and sample and channels and whatever. Total values. That's a very bad name. Let's see. I'm so looking forward to the better programming experience we will have when AI is put in our compilers and all the tools we use. Like what OpenAI does, but better. Okay, I think this is it. We have 68,000 audio samples, which are mono. And then that's it, isn't it? This one we can just create from the list of samples. Okay. Yep. One channel for now. Now our audio is in the analyzer. No, it's not. Now it's in the analyzer, and now we can tell it to analyze. Yeah, I want to set the window size to maximum actually. Full audio clip. Here. Okay. smallest window. Make window. Full window maybe. Oh. Yes. Audio. Start and length. And it's gotta be rounded. Okay. Now we tell it to process the whole window. I think. It's a bit convoluted because it's a sliding window that I don't really use right now. I could make a new class or whatever to simplify stuff. When I have two classes to manage, it's not that good either. We're done with this and this and this. So no. Yeah, just this one call, I think. So step 2. Okay, this should do it, I think. There's another interface for audio samples. It's this one. So we could also just implement this one. Yeah. It's too many different classes. What's the thing by OpenAI called? Open Codex? What was the name again? The thing that programs for you. We kind of need that, but we need it in a better way. OpenAI, what is it called? OpenAI Codex, right? Yeah. Yeah, the system that translates natural language to code. But I still question whether they are able to do this. They are able in some cases, but their foundation is not right. Neural networks are not the solution for AI. It's true. Neural networks are not the solution. They're just a shortcut that seems very impressive unless it fails, etc., etc. Basically, neural networks are one mathematical trick, but we can find a generalized mathematical trick that works in more cases. I'm sure that this is true. There is something better than neural networks. We just have to develop it, find it, discover it. Okay, come on, bro. Now we should be... Okay, it's just a technicality. Okay, now I think we have analyzed the audio, and we can... I mean, we should have an image, right? We should definitely convert this to an image. Yeah. Let's put the image stuff back in. I want to see frequency images. I have ADHD, I need gratification instantly. I need to see images. All these numbers are just not doing it for me. I need images. Okay. Oh, I think this code could still work. We just store more data over time. The window is bigger, but this function, which is made for a smaller window, should actually still work fine. Yeah, okay, sure. Okay, image column. Okay. So image for window. Oops. Mix buffer. Yep. No, we assume they're already measured. Oh, we need to specify how many pixels we want per time interval. Pixels per second. Okay, and okay. go for time equals window start. We go to why is it so complicated? No, wait. Okay. We have the length in time, which is the length of our window. And then we have a number of pixels, which is the length in time times pixels per second. Exactly. Yeah, now we're getting somewhere. And then we say for I2, no, yes, we get this number of pixels we need. We add another column, which comes from this function here. And yeah, that should be it actually. Our new time range is current position divided by pixels per second. And now we're in the time domain. And we add start of our window. Yeah, I think. But we need this one. And the next one. Let's say we don't do overlap for the visualization. And maybe. Oh, this is the indication of a bracketing error. And in fact, I forgot a bracket. Okay, this is almost done. If you can do calculations like this, like how to multiply and add and divide and stuff, you are a programmer. You can figure this out live. You are destined to become a programmer. Because you will have to do it over and over again. You will have to write low-level code that actually calculates something with plus and minus all the time, all over again. You can never forget the lower levels of coding. You will always need them again, whatever you coded. It's how it is. Okay, are we seeing an image? No, because we didn't call the function. Let's see. Image for window. And pixels per second are 100. Is it an endless loop or something? Because there's no way this could take this long, actually. Let's ask the profiler. Profiler will tell us what's going on. Yeah, I think it is an endless loop, and sadly the cancel button is broken. I know this and I have to fix it, and it's probably going to run out of memory because there's a nasty bug, and the only thing that helps is restarting the Java process. Okay, something's wrong here. Oh, I know what is wrong. Yes. It's not an endless loop, it's just way too big. The value we have here is in samples, and now we have to convert it in seconds. And there's that. My window, my cam will be back in a second. It's being started as one of the modules here. No, maybe it's not. It's not marked as auto start. There we are. And where's my goal? Where are my goals in life? Here they are. Okay. Yeah, this cancel button, I should fix it. It's not hard to fix, it's about thread management. I'm so proud that JavaX calculations can be interrupted, and then I kind of broke the feature. If it was working, we didn't have to restart this thing now. Okay, it's computing. Come on. Okay, image is black, but at least it has the right number of pixels, and I'm sure there's a scaling problem. Just like you need to apply some gain, something. Let's see. Image column. Okay, let's take the raw image column. Just the floating point values. No, we're normalizing them to a value. So it should never be black unless it's completely zero. And then there's a bug. Okay. Okay. Yeah, it seems to be all zero. Maybe the oscillators weren't actually oscillating. That could be a thing. Intensity. Okay, this is a good debugging function. It shows me how much time was actually scanned by each oscillator. So we print this, and we will be much smarter after this. Yeah, it's 0, so it didn't actually scan. Whatever. I thought the step 2 function is doing this. Guess it's not. What does the step 2 function do? Yeah, this finds out what is to be done for one audio sample. Oh, but okay. Right. We want to go to the end of our time range, not the beginning. Right. Okay. I think this was the problem. Maybe we get an image now, which is not all black. Maybe. Or maybe not. Okay. Window bounds is okay. That's the number of samples at 48 kilohertz. Oh, there's a function called start oscillators, and I believe I did never call it. What is current sample? Right. 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 So we simply call start oscillators. Yeah, I think this will fix it. Come on, you know what I want. Okay. Oops. What is this? It's an image, alright. I'm not sure it's the image we were waiting for. Because it's all the same thing, isn't it? And yeah. Actual relation set. Average. We're taking an average. We don't even need this at this point. Yeah, let's do a simpler thing actually. We just find the one period for this one point in time, and take the amplitude. It's a tree map, so we can find a range can be compared to other ranges. Yes. It's compared by the start, and if the start is equal by the end. So what we want is a search in a tree map, and we want the lower. Let's ask Gazelle while you're searching a tree map. Map lower. Here? No. Okay, give up. I look it up. Okay, navigable map. Navigable map. Something like lower key. Strictly less, but I don't want less. I want floor. I want equal or less. Floor key. Okay, I found it. Find right period. Oh, actually just the time range we are after. Right, okay. Okay. And no need for this crap, we just return the amplitude. And that's it. That was nice and simple. The amplitude is 2 get this, take the first channel, take the absolute value. And score. Aha. Okay, that was easy. Next try. That is still shite. But we can turn shite into gold. I'm very certain. with a little shite polishing. Image for window. There must be something wrong here. Let's print our time range because that's most certainly incorrect. It doesn't look like that bad, but we have a different time range. In this class, it calculates in samples, not in seconds. So we multiply with the sample rate. What am I doing there? And that should be the thing. I think now we could be getting a better image, actually. Yes, that looks way more like actual audio data. Good. It has a melody, see here. It has a pause. And it has, this is more high frequency audio. This is less, so this is an S sound or something. What did we say again? Recognize this is what we said. What the voice said. Recognize. Yeah, somewhere in here there are all the sounds. This must be this. This. What's confusing to me is there should be like S sounds and vowels. And the S sounds should have higher frequencies and the vowels should not have. So I'm not even sure where in the image, which part is. Let's just say recognize. What does that look like? The same? No. It cannot be the same thing. What? Different URL? Huh? What is what? Why am I seeing the same image for different input? What? Tell me that ain't so. This is the exact same thing we were just looking at now. Try this here. Yeah, that is definitely the same image now. Yes. $63 kilobytes. Also 63 kilobyte.
Recognize.
Yeah. Huh? can play audio, right? Play wave. Man, what is this bug? Oh man.
Recognize this.
Oh yeah. Okay, maybe our analysis is doing funky stuff. But no, I mean, what? Let's use some completely different. Let's use the audio file we used to have. Where is it? Leave this one. Audio file. Peter, can you hear me? Okay, that's the one. That is an OGG file. Can we read OGG files? We should be able. Or whatever, let's use another input. One, two, three. Well, let's use the same word twice or 3 times. Hello, hello, hello.
Hello, hello, hello.
Hello, hello, hello. Sounds like a weird Russian accent. Huh. Okay, this one has to be different than the other image.
Recognize this.
Sure. We're getting the same image every time. Oh. The WAV file has a bad name. It's writing to the same WAV file all the time. Okay, this is a stupid little bug that cost me like however many minutes. I think it has no extension, so yeah, I think. Okay, I think I got it now. Yes. Yeah, the file has no extension. Okay. That was a stupid little bug. Now it's gonna work. Okay, that should be our hello, hello, hello. Hello, hello, hello. And in the end it sounds different. Okay, because the melody is like changing in the end. And now let's try our recognize. This would recognize this. And this one is just to recognize. Or was it?
Recognize.
Recognize. What is this here? Oh, this is silence. Because of the normalizing, if everything's really silent, the little hiss you have is blown up to look like a lot more. So it's kind of a funky normalizing, just for every column separately, which is kind of nuts, I guess. But anyway, yeah, what if we do the normalizing later? Oh, that's too much coding work. Okay, we want to convert this back into audio. So I just take all the frequencies and all the periods and render them back into audio. There are going to be too many frequencies because I take 12 tones per octave. I'll take the piano keys, and there's so much overlap. I think you would normally just take the octaves, or I'm not actually really sure. The thing we're modeling is inverse FFT. Go from frequencies back to audio. Why is it in German? Who reads German? Okay, fast Fourier transform. IDFT. The elegant thing about the Fourier transformation is that the inverse is the same as the forward transformation. They are basically just the same thing. Probably what I want to do here is it has been done somewhere. I mean, let's just experiment. I mean, whatever. Let's do the raw thing and just take all the periods. Yeah. Let's mix all the frequencies together, whatever. Let's try that. Okay, lots of other things here. It's all part of the recognition by compression framework. To audio. And what we get is it's an array of levels, just audio samples. And it's similar to making an image, but it's completely different. Okay, sample range. First we convert from time to samples. Let's make a cool new function, or extend a function. Let's make the ifloor function work on ranges, because that's very elegant. Yes. Mm-hmm. Function extended. Where is my source file? Okay, that's our sample range. Now we can make the array. There. We go over the time range. And we go over the oscillators. I need a drink. We need to know where in its period each oscillator is. Yeah, we have an iterator. Oh man. Oh, stuff is so complicated. Oscillator. And we have a current value. Okay. You see settable new Java X modifier. Map oscillators. This and this. And don't even need that. Oh yeah, I can have it somewhere. Periods. What are those things? Yeah. Floor key. That was one. Floor key. Time range. Okay. If we have any period at all recorded, except the value according to no, let's forget this one. We calculate the value later. I think this is pretty much okay for now. Next period. Higher t period, okay. In the end, we have to sum all the oscillator values we get. Samples is sum, okay. And for each frequency, we look at the periods. Oh, we need the intensity that was recorded. Right. Okay. Okay. That intensity. If there's anything we take the first channel, we take the absolute value, and that's our... No, we need to do the phase also. Of course, we need to do the phase. We have a complex value, C. And we can now decide, actually, we can render sine waves or square waves. I'm not sure which is even correct here. We should do square waves because we are sampling in square waves, but it still may not be very good. Maybe this whole thing doesn't really work unless you sample better. You have to sample sine waves maybe to make that transformation back into audio work. And right now I'm sampling square waves, but we will see. Let's do sine and cosine, whatever. Sine of... Yeah, what is our phase? Our phase is... it's not that difficult. It's just a time. Yeah, what's our t? T for time is... in samples, actually. Time range start. Sample range start. And here we should also use sample range, in fact. sample range start. Now here, yeah. Okay, t is time in samples. And we subtract the start of the current period. That's our phase, and we have to divide it by the frequency or the interval effect. Length of period in samples. And we have to multiply with 2 pi, of course. You knew that, right? That we needed that. Holy moly, is this correct? Huh. I'm not completely sure. It's relatively reasonable. Let's see. Okay, we take the real part of the complex number, and we multiply with the, let's say, the sine wave, which is probably wrong. No, it must be the cosine, I think. Phase, and take the imaginary part, and something like this. Sine of phase. There's maybe a wrong, wrong sign here. There should be something like this. This is going to be hot garbage, probably. Let's see. Probably have to declare first and then make use of. Okay, floor key int range. Yeah, okay. Whatever. An int range is not the same as a double range, because one has more precision than the other. That was the wrong switch. Okay. Make a synonym. Floor key. I think there was a problem in the complex class. Yeah, it doesn't have getters. It should have getters. Now it has getters. Okay, getting there. intensities, 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 and oh, did I do it again? I broke something, I guess. Nope, not sure what. What? Factor. A factor needs a default. Okay. Okay. We need to call the function to audio.
Recognize.
Thank you. Um, let's use sample ranges here, not time ranges. There. Let's see what we generated. Oh. High floor. What did we make?
Recognize.
The Franken audio. That was wrong. And we need to move to the next period, actually. I forgot that one. Next period. Oh, you have to give it the time. Okay. Okay. If there's nothing, then there's nothing. If this is out of the range, we go to the next one and we maybe do it again, I guess. Just to be safe. Yeah, okay.
Recognize.
I will. Okay, rendered some audio. Let's say we normalize the audio. Audio norm. We normalize to industry standard 16-bit samples, and then we convert to shorts, or we could directly put it into an audio file. Wave file, right? Double to wave. Short area wave. Short area to mono wave. Double array to short array, and we use round and store in a new file. Dot restored. And then we play the audio file. Need one more conversion function. Short to double array, that's almost the right thing. Just the wrong direction. So we say double short or something. Nope. Yes. Normalize short arrays. Nice, nice, nice. Double to short array round. Clamp to short. We want to clamp, I mean, handle values that are too big or too small. properly. Forget this one. Compiles. And we have made a wave file. No, we have not. What did I do? Must have done something bad.
Recognize.
Oh, one extra bracket here. Double to short array. Almost there.
Recognize.
Now we should have a wave file here actually of dubious content and bad naming. Dot restored. Let's open it, right? And the result is here. Do we dare to play it? Maybe reduce the volume first. Here goes. Oh, oh, it's not good, but it's not wrong either. Here's something. It's certainly the right sample rate. It's just kind of distorted. Huh. Are any obvious mistakes I made? I don't think so. First thing to try the sine and cosine thing. Let's try if there's a minus instead of a plus. Yeah, we can actually properly calculate this. Wolfram Alpha help us out. Sine of x, show me. As we all know, sine of x starts at 0, goes up here. What is the thing we are sampling? It's a square wave and it starts at 0. So the thing we're sampling, yeah. The thing we're sampling is basically this. It starts here, there, yeah, starts up here. see. Oh, I'm trying to make Java comments, but I don't think Wolfram Alpha knows these. Okay, this is a sine wave moved. This is the same as cosine. Okay, x minus pi, that's the same. So in fact, we should really be using sine and cosine. We just use the square. We use one of these. We can express sine as cosine. We can express cosine as sine. We do not care. But this is phi angle, and imaginary one is the same minus this. Yeah. Okay. Okay, whatever. It is the same thing we just did, I guess. I'm not sure. Oops.
Recognize.
Doesn't have reload. No, does not. Recent files. What? Did I break Audacity? How did that happen? What? Okay, anyway, we should just play the wave file. Play wave. Play it. Play. I think Audacity crashed. That seems like it. Oh no, I have to. Oh god.
Recognize.
Okay, now we try to use a square function to render the audio. Maybe it's a good fit because we are sampling square waves. So why not? Where are my windows? So why not render a square wave? Let's check if this is correct here. t minus period start is it simple as this started time by. I think this line is correct actually. So cos square wave. Cos square wave. Huh? Avoid band and at commenting. Oh my god. Something with a YouTube channel. What is it? Sometimes comments don't go through. All the crap comments I get go through. Strange. Okay, new function, cosine. Like cosine, but square wave. No. So we just divide by pi, of course. We get the fractional part. Then we know where we are in the. Now we divide by the whole period, which is this. So it gives us 0 to 1. It's the phase, and we just return 1 or minus 1, depending on where we are in the phase. Okay. And let's try the square waves then, right? How bad can it be? Audio rendering in square waves. Take 1.
Recognize.
Yeah, it is just as crappy as the other one. So that was not the issue. The issue is probably my frequencies. These piano frequencies I use. What if I only take octaves? That would be the next thing to try. Instead of 88 frequencies, I just take whatever comes out, 7, but that's such a small number. Can that be correct? We'll see. Perfect. We just select a few of these. Oscillators to reuse, render. And it's a collection of oscillators. By default, we use all of them. There. And then we select our oscillators. I can simply use every 12th of these. Yeah, let's say whatever. I0. Let's do something different. Let's say so this is an octave. Apparently you can't comment here. That's really odd. Very odd, in fact. No idea, man. So my loyal fans cannot comment on this video. That's a joke. That is seriously a joke. I don't know, man. So use those that are divisible by 12, which should give us the octaves. And yeah, using frequencies. Tree has key map. Special smart map. It is iterable. Oh, it's iterable, it's not a collection. Okay, okay. Render. But it is a collection, basically. No, it's not. Doesn't matter. Java technicalities. Okay. Alright. We should hear something. No, we don't. No, we should hear something. Now we should hear something. What am I doing here? Wait a minute. This should not be hard. No, we should hear something. No, we do not. Oh God. Now we should hear something.
Recognize.
Okay, what if the frequencies? We used 27.5 hertz, 55 hertz, 110 hertz. Yeah. Used all the octaves. The result is not worse than before, I think. Let's listen again. If the result is not worse, we have at least spent less energy because we are using less frequencies. Please. It still sounds bad. What if we now go back to the sine waves? Here, proper sine waves.
Recognize.
Okay, there are two possible reasons for this. A, there might be a bug. The code might just be buggy. Maybe the phase is wrong or something. The other option is that the method isn't sound. If I sample all these piano frequencies and I go from there back to audio, maybe that's not feasible, but it can't really be correct, because what is the FFT doing? It's the same thing. They also sample frequencies. So do we need to select the frequencies differently? Maybe not here this, but maybe we need to go linear, but that doesn't make any sense. Do we need the frequency 30 plus 40 and then 50 and 60 and 70? We're never going to get to the high frequencies. It makes no sense. The fact that this is a geometric progression, it sounds good. It's the only way I can imagine this. This has to be a geometric progression. Let's do something else. Let's do just every other frequency. 6 per octave. Let's test that.
Recognize.
And now the question is it even using our oscillators? What if I say no oscillators? Then things break horribly. That's helpful. Oh, because I have nested comments. Okay. Give me sound.
Recognize.
Okay, that was a silent wave. That's good. So if I have no oscillators, it's silent. Okay. If I take 6 per octave.
Recognize.
I get the same crap results. It really doesn't matter that much. If I take 2 per octave.
Recognize.
It doesn't seem to make much of a difference. It's kind of interesting. Let's cut at a certain frequency. Let's go with all the frequencies. No, let's go with the octaves. And let's cut off at a certain frequency. Max frequency. And our max frequency is, what is it? Let's go really low. Let's go like frequency 400 hertz. Cut off at 400 hertz. What's that sound like? Oh! Needs a new function.
Recognize.
Okay. Okay. And how about we take only the high frequencies? Let's say we start at 400 and we stop at the maximum. We should have less bass frequencies. Let's check that. Yeah, it was only 4 frequencies left. Not that much, obviously.
Recognize.
Okay, it sounds tinny. That's reasonable. We're only using 4 frequencies because I only use these octaves.
Recognize.
So almost the last remaining theory is that there is a bug. We should simply test very simple audio inputs and see what the system does with it. Because we can wrap this whole thing in one function and it will just say restore audio. So we can it will analyze and restore the audio so we can check how good the restoration is. That we should do next, definitely. And maybe, I mean, it has to be solvable. The only last thing we might have to do is do proper sampling with cosine and sine instead of square waves. I think we can get around that. I was using this other tool first, written by somebody else, that also did frequency images and audio restoration, and their restoration is good. And it's based on DFT, so DCT, whatever, based on the regular frequency transformations, which are similar to what I do. Yeah, we should figure that out. Anyway, that's enough for now. Bye.